Hi everyone. In this video we're going to be working on the derivatives of exponential functions. So continuing our basic study of derivatives and finding out how to find even more derivatives, so even more tools in your arsenal, things to remember that are really foundational that we're going to use the rest of the semester. But this time, exponential functions. So first, I want you to remember the derivative is the slope of the tangent line. And so to give you a picture of what I mean when I say that, let's say this red curve represents my function, and the derivative is going to be the slope of this tangent line at any point, right? So I can specify some value for x, and then the derivative tells me what is the slope of this blue tangent line. Okay? Second, remember that there's a difference between what we call power functions and what we call exponential functions. And so, for example, for a power function, we might call a power function p of x a power function. If it's like x raised to some power, like x to the 7th is just one example of a power function you could come up with. And an exponential function, that means something different. And so an example of like an exponential function might be the function 7 to the power x. So clearly the difference between these functions is with a power function I have my independent variable as the base, and I have just some constant as the exponent, whereas with an exponential function my base is actually just a constant, and the exponent, the exponent, that's going to be where my variable lies. And so know the difference and be able to recognize the difference between the two. This is a very important skill that hopefully you mastered in your business math class, but I just want to point out the difference between these two before we move on. Okay, now that we've refreshed, I want to point out two functions that I think are particularly cool. So number one, we have the function y equals 1/2 x squared. And the reason I think this function is cool is because whenever we take the derivative of y with respect to x, so the derivative of this function, power rule just tells me to bring down that 2, and then my new exponent's going to be 2 minus 1, which is just 1, and so 2 and 1/2 cancel, and actually the derivative of this particular function is just x. So that means the slope of the tangent line of this curve anywhere is just the same as the input. And so again, my horizontal axis is my x-axis here. So when I let x equal 0, the slope of my tangent line is 0, so it's flat. When x is equal to 1, the slope of this tangent line is 1. When x is equal to 2, the slope of this tangent line is 2. When x is equal to 3, the slope of this tangent line is 3. And of course, whenever x is negative, you're going to have negative slopes for your tangent line. And so I think that's just kind of a neat property that a function can have. And really, this is the only function that has that property, short of just adding a constant to it, right? Short of moving this red curve just strictly up and down. But that kind of makes this function unique. Now, there's another function, similar property, but quite different actually. And it's this function, y equals e to the power x. And just as a reminder, e is a constant, and e has the value of about 2.718 or so. And what's sort of special about this, I want you to realize the difference. With that function I just showed you, the slope of the tangent line, or the derivative, was just the input to the function. But actually for this special guy, what makes him special is that the derivative of this function anywhere is just the output of the function. Okay, so let's maybe just show you in Desmos kind of what I mean. And I'll change my function now to e to the power x. And if I allow my y-axis to be my vertical axis, so the vertical axis represents the values of the output of the function. Whenever the output of this function is 2, the slope of this tangent line is 2. And whenever the output of the function is 1, the slope of the tangent line is 1. And whenever the output of the function is well, so between 1 and 0, I don't have a finer subdivision. There we go. Whenever the output of the function is half, the slope of this tangent line is 1/2. And whenever the value of the function is like 1/4, like right here, then the slope of this tangent line would be 1/4. Okay, and so as this function goes up in value, so does the steepness of the function, or so does the slope of the tangent line. And so again, that's what makes this function unique. There's no other function like this that has this property, except for if you scale the function by some scalar. But these two functions are cool in that way, right? They have these special properties that you should be aware of. Now it turns out, if we have exponential functions with different bases, like other than that e, they're not quite as cool. They don't have the same property. They're still kind of cool, and I want to summarize. And what I have put in this blue box represents things that you as a student must memorize. What you must memorize is whenever you have the derivative of e to the power x, so the exponential function with base e, that derivative is just e to the power x. And so that's a remarkably simple derivative. If you were to take the derivative of the exponential function 2 to the power x, now it's actually natural log 2 times 2 to the power x. So notice this is just a constant. So in other words, we might say that the derivative of 2 to the power x is proportional to the output value, but it's not exactly equal to the output value. Same thing for 10 to the power x or any other base. So I use lowercase a to represent just any other base of an exponential function. It's always going to be such that an exponential function has a derivative that's proportional to the output of the function, and that constant, that proportionality constant, if you will, that multiplier that comes out in front is always the natural log of the base. And I just want to point out this, that the exponential function with base e is actually not exempt from this rule at the bottom. So it looks like this and this are different derivative rules, but in fact they aren't. What I want to point out is that if I take the derivative with respect to, or the derivative of e to the x, this is going to be natural log of e times e to the x. But then I want to point out that natural log of anything is actually referring to the logarithm with base e. And so if I take, the logarithm of base e of, e itself, that's just the number 1. And so this simplifies to 1 times e to the x, which is then just e to the x. So, this is all self-consistent, is what I'm trying to point out. This bottom rule does not in any way contradict the first rule. It's just that that number e, the whole reason that number is special, the whole reason we have assigned, 2.71828, one of the letters of the alphabet, is because it has this very special property. Okay, so that's something to remember here. And now the rest of this video is going to follow this following format, and we're going to work a bunch of examples where I'll show you how to do an example, like example 1 here, and then I want you to try the practice. After you see the example, go ahead and give the practice a try. That means pause the video when we get there so you don't see the solution before you really give it your best attempt. And then once you've attempted the problem at least, you can look at the solution and just check to make sure you didn't have any mistakes, and then we'll move on. There's about 10 problems like this. So my first example, I have the derivative of 2 to the power x times x squared plus 1. And so I have a product of two functions, right? And so I'll name this 2 to the x my f function and this x squared plus 1 my g function. And my product rule says that when I'm trying to take the derivative of f times g, what I'm going to have to do is set this equal to f prime g plus fg prime. And basically, to use this formula for the derivative product rule, I need to find what is going to be f, what is f prime, what is g, and what is g prime. So f is going to be 2 to the x. G is going to be x squared plus 1. F prime, well, that's going to be 2 to the x times natural log 2, right? We just learned that. And g prime, this is going to be a power rule thing. It'll just be 2x. And so putting this all together with my product rule formula, I find that the derivative I'm looking for, my solution in this case, is going to be natural log 2 times 2 to the x times x squared plus 1 plus 2 to the x power times 2 times x. And there's different ways that you might, clean this up to make it look a little bit nicer. It's really up to you if you want to group things. If you just write this as an answer on exam, it would be totally fine with me. So this is the point where you pause the video, you try practice number 1 on your own, and then when you're ready, start the video again, and you can see this solution. So at this point, I'm assuming you've worked the problem on your own, and I'll show you the solution to practice 1. Well, this is going to be my f function, and this will be my g function. And so whenever I write f prime g plus fg prime, f prime should be natural log, that's ln, of 10 times 10 to the x. G is 5 minus 3x cubed, plus f is 10 to the x, and then g prime is going to be negative 9x squared. All right, so there's your solution. Moving on to example 2. So follow along as I show you how to do this type of problem. We have the derivative of e to the t divided by t squared. And in this problem, I see a quotient. And so, of course, I have to use the derivative quotient rule. And that's telling me that if I'm taking the derivative of a quotient of functions, f divided by g, then this is going to be f prime g minus fg prime divided by g squared. Now f, the numerator, is e to the t. So that means f prime is also going to be e to the t, because that's a nice, easy derivative. G, my denominator, is of course t squared, and g prime is going to be 2t, using the derivative power rule there. Now f prime g will then be e to the t, t squared, minus fg prime is e to the t, 2t, divided by g squared. Well, that's going to be t squared squared. And so just to clean this up a little bit, you might write something like t squared minus 2t times e to the t over t to the 4th power. Nice. By the way, you could also write this by factoring out 1t and canceling it in the denominator. You could write this as t minus 2 e to the t over t cubed. And just as good. Same correct answer. Okay, this is the point where you take a moment and you work practice number 2 on your own. Give it your best shot, your best attempt. Follow the guidance of this example and see if you can work practice number 2. At this point, I'm assuming you've tried to work practice number 2, so I'm going to proceed with the solution. So again, quotient rule tells me this is going to be f prime g minus fg prime over g squared, where f is my numerator and g represents my denominator. So f prime is going to be 3e to the t. G is going to be t. Minus f is again my numerator, so that's going to be 3e to the t. And g prime is going to be the derivative of my denominator, which is just 1. My denominator is t, so I divide by t squared. And then factoring out 3e to the t, this will become 3t minus 1 e to the t over t squared. There's your solution. Example number 3. Here we go. So maybe a new feel for the problem. We're taking the derivative with respect to y of y to the 5th power minus y to the 3rd power divided by 3y. And again, we have a quotient of two functions. So we have to use the derivative quotient rule. So I write f prime g minus fg prime. And by the way, when I'm working a problem, like on a math exam, I always write out the quotient rule because it's difficult for me to remember. So I'm going to write it out before I actually work the problem. And again, f represents my numerator. And so f prime is going to be the derivative of my numerator. So it'll be 5y to the 4th power minus 3y squared for f prime. Then I multiply times g, which is my denominator, 3 to the power y, minus f, which is y to the 5th, minus y cubed, times g prime. Now g prime is the derivative of my denominator, so I write natural log of 3 times 3 to the power y. And I divide the whole thing by g squared, which is 3 to the power y all squared. Okay, now in the numerator, I'm going to try to collect all of the polynomial terms inside a parentheses. So I'll have like y to the 5th, which is actually negative y to the 5th, because I need to distribute in that minus sign. So I have like negative y to the 5th plus 5y to the 4th, and it occurs to me that I also have a natural log 3 up here. And maybe I'm being a little bit too picky right now about cleaning up your answer, because we've already technically come to the answer of the derivative right above here. But I'm just trying to show you, if you wanted to make this a little bit nicer, a little bit more simplified, you might write negative natural log 3y to the 5th plus 5y to the 4th plus natural log 3y to the 3rd power minus 3y squared all times 3 to the y power. And in the denominator, I've got 3 to the y power squared, and 3 to the y power squared is like 3 to the y times 3 to the y. But then you might say, hey, we have a 3 to the y here in the numerator and a 3 to the y here in the denominator. So I'll just cancel those out. And after that cancellation, this is what you should be left with. And this is your correct answer for example 3. Now, after following along in example 3, this is the point where you pause the video and you practice and give your best attempt for practice 3. Now I'm moving on, assuming you've given this your best shot and you're ready to check your answer. And it looks like, again, we're using the quotient rule. So I always write f prime g minus fg prime over g squared. F is the numerator. So f prime is going to be the derivative of my numerator. And my numerator actually has a couple terms here, so this is going to be a bit tricky. Hopefully it was a good challenge. The derivative of 2 to the y will be natural log 2 times 2 to the y. And then I'll write minus 4y for the derivative of negative 2y squared. And so this represents f prime. And then I multiply by g, which is my denominator, 5 to the power y. Okay? Next, I do minus f, which is my numerator, 2y minus 2y squared, times g prime. Now, g prime is the derivative of my denominator, so I write natural log 5 times 5 to the y. And then I divide the whole thing by g squared, which is going to be 5 to the y times 5 to the y, will be, in other words, 5 to the y squared. And then you say, well, one of those 5 to the y's is actually going to cancel with the 5 to the y that appears in my numerator. So this is pretty much as good as I want to make it, right? So if it's complicated like this, I don't particularly care if you simplify. I'll accept this as a correct answer on the exam, because even though this isn't perfectly simplified, you have already taken the derivative, and so this one's good enough for me. Example 4 says we're taking the derivative of e to the power x squared. So this is actually a composite function, right? So on our composite function, we might write something like y. Let me write the word composite function. Y is equal to e to the power x squared. And if I just let u be defined, lowercase u, as x squared, then this is sort of leading me to a simpler expression. This is y equals e to the power u. And so if you can't tell what I'm doing right now, whenever I see a composite function, I use the derivative chain rule. And what the derivative chain rule tells me is if I'm trying to find the derivative of y with respect to x, then I can rewrite this as dy du times du dx. And I can just choose u to be some simpler function of x that I see appear in my function, in my function y. So I can write y as equal to e to the power u. And now I'll switch pen colors so that we can see for this dy du, I'll start right here, dy du. Well, the derivative of e to the u with respect to u is just e to the u. Okay, so far so good. Then we look over here and we say the derivative of u with respect to x. Well, if I have this, u equals x squared, then du dx is going to be 2x. And putting it all together, we have dy dx is equal to e to the u times 2x. And what I really want from my derivative, I want my derivative to be in terms of x, because u is just something that I made up. And so to get rid of this u, we just have to substitute that with the definition that we gave u in the first place. So in the first place, we said that u is just x squared. So this is going to be e to the power x squared times 2x. And that's what we're looking for. Now that you've seen example 4, I invite you to try practice 4 on your own. So give that one a shot. This is the time where you pause the video and give yourself time to work it out. And now I'm going to assume you've already given this your best shot, so I'll show you now the correct solution for practice 4 so you can check your answers. And in practice 4, this is a chain rule problem again. So my outside function is 2 to the power x. Then my inside function is going to be 4 minus 3x squared. And taking the derivative of the outside function gives natural log of 2 times 2 to the power 4 minus 3x squared. And then after that, we have to multiply by the derivative of the inside function, which for us is going to be negative 6x. So that right there is your solution for practice 4. Okay, last pair right quick. If you look at example 5 here and follow along, we have the derivative of square root 10 to the power t. And you should remember, always remember this, that if you take the square root of something, that's just equal to that something to the 1/2 power. So let me rewrite this as 10 to the power t all to the 1/2 power. There's something else I want you to remember as well. That something else is that if I have x cubed squared, well, what is that? X cubed squared is just x cubed times x cubed. Well, what is x cubed? X cubed is just x times x times x. And so this is actually x to the 6th power. And it turns out whenever you take two consecutive constant exponents like this, where right here I have x cubed all squared, I can just multiply 3 times 2 to get x to the 6th power. And so that's a nice, easy way to simplify this. How does that apply to my situation over here in example 5? Well, that means this, I'm taking two consecutive exponents like that. Let me just multiply them. So I have 10 to the power 1/2 t, right? I've now multiplied the 1/2 and the t instead of taking 10 to the power t to the power 1/2. And now, this is going to still be a derivative chain rule deal, where we say, let me define u as just being 1/2 t, and that means du dt is equal to 1/2. And that means my dy du is going to be natural log 10 times 10 to the u. And putting this all together, let me go ahead and rewrite the derivative chain rule. It's saying the derivative of your whole function with respect to your independent variable is going to be dy du times du dx, where I get to choose what my definition of u is. And in this case, we chose u is 1/2 t, because I sort of saw that 1/2 t nestled in there. And now that I know these values, I can say that my derivative of this whole function altogether is going to be dy du, which is natural log 10 times 10 to the power u, times du dx, which is just 1/2. And excuse me, because I've made a little writing mistake. I would say typo, but this should be dy dt, because now my independent variable for this problem was t, wasn't it? So in any case, this is going to be our final answer. Oh, and a mistake I frequently make, as it turns out, is I like to leave u's hanging out, but never do this, right? So we want actually this derivative in terms of my independent variable t. So let's write this, but now we're going to replace u with 1/2 t. So I'll write 1/2 t there. And the answer is natural log 10 times 10 to the power 1/2 t times 1/2. Okay, this is the point where you pause the video, you try practice 5, and give it your best shot there. And then once I'm done erasing this, I'll assume that you've given it your best attempt and you're ready to see the solution. But really, I encourage you to not skip ahead to the solution until you've really tried and really poured out some tears into this, because the way we learn is through struggle. It's not fun and it's not comfortable, and it definitely takes time and practice, but that's how you're going to get better at math, just like with anything else. Okay, now let's try practice 5, which is an application of the derivative chain rule. And in practice 5, we have the derivative with respect to t of e to the power 5t all to the power 3/2. Sorry, I just realized this is not an equality, but this is after having taken the derivative. So I'm not going to write an equal sign there. I'm going to write an arrow. Okay. Okay, so back to here. this is the same thing as the derivative with respect to t of e to the power 15 halves t. Now, why do I say 15 halves t? It's because if I choose to take two exponents consecutively, I can just multiply the two exponents, right? So where I have e to the power 5t to the power 3 halves, I'll just multiply 3 halves times 5 and I get 15 halves. So now this is a chain rule problem, and my answer here is going to be e to the 15 halves t times 15 halves. All right. So hopefully with this and with a lot more practice, you will be a master at doing sort of exponential derivatives and using the exponential derivative in the context of the product rule, the quotient rule, and the chain rule for derivatives as well. So I'll see you guys and have a great week.